All right, moving on to solids and liquids. Says the condensed phases, being solids and liquids. In the condensed phases, the particles are much closer together. Because of this, they interact much more strongly than particles in gases. And so we can look at it from both ways. Why do they interact more? Well, the attractive forces are stronger, which pulls them in closer together in the first place. So kind of those two things go together. So kinetic molecular description of liquids and solids, take a look on page 448 at table 13.1. We have a list of the observable properties of solids, liquids, and gases, how they're similar, how they're different. We can also see in the figure there just below that the arrangement of the particles. We've talked about this before, so make sure you know the difference between solids, liquids, and gases, both in terms of their particles and how they interact and their observable properties. A little vocabulary term here, a process where a liquid can mix with another liquid is called miscible, or miscibility, the ability of a liquid to mix with another liquid. The opposite of this, immiscible, immiscible, is where two liquids don't mix. So an example of immiscible substances would be like oil and water. Right, what's crucial in this unit is understanding the attractive forces between particles and the strength of those attractive forces, giving rise to the properties of a substance. So let's look at the attractive forces between ions, say in an ionic compound, and molecules in a molecular compound. So we've talked about this before, the attraction between oppositely charged particles. The force of attraction between oppositely charged particles we can determine using Coulomb's law. So once again, it looks like this. F being force of attraction, we have some constants, K. Of course, Q1 and Q2 are the charges. Charges of the ions, if it's an ionic compound that we're looking at, could be kind of partial charges of the opposite ends of polar molecules as well. And then R is at distance technically between the center of the bonded atoms, or I guess the centers of the molecules. So it's how far apart the attracting bodies are from one another. So based on the above two factors affecting the strength of an ionic bond are, of course, the magnitude of charge. So the greater the charge magnitudes, technically we talked about the product of the charge magnitudes, the stronger the force of attraction. And then the smaller or shorter the distance between the attracting bodies, the stronger the force of attraction as well. So those are two factors that affect attraction between oppositely charged particles. The term we use for that, by the way, attraction between oppositely charged particles, is known as an electrostatic attraction. So you ever see that term electrostatic, we're talking about charged particles. All right, specifically the attraction between molecules are known as intermolecular forces. That prefix inter means between. So we're talking about attraction between different molecules. So it says the force of attraction between separate molecules are called intermolecular forces. However, the force of attraction between atoms within a molecule are called intramolecular forces. That prefix intra means within. So we're talking about here covalent bonds. Now, something that's very, very, very important is that all types of intermolecular forces, any of them, are much, much, much weaker than intramolecular or covalent bonds. Let me give you an example of this. So let's say you take some water and heat it up. What's going to break first? The attractive forces between the molecules or the attractive forces between the atoms within each of the molecules? So it says the energy needed to break the covalent bonds in water to form separate hydrogen and oxygen atoms is 927 kilojoules per mole. The energy needed to separate a mole of liquid water molecules from one another and turn them into individual water molecules in the gaseous phase is about 41 kilojoules per mole. So yeah, when you heat up water, you are not breaking covalent bonds. You are breaking the attractive forces between the molecules. Just looking ahead, course, in this case, that would be hydrogen bonds. There are three types of intermolecular forces. They are dispersion forces, dipole-dipole forces, and hydrogen bonding. So let's just go in the order of the notes here. First one listed, dipole-dipole forces. The prefix di means two, pole, opposites. So a dipole is a molecule that has opposite ends. So dipole-dipole forces are forces of attraction between the opposite ends of polar molecules. So it says permanent electrostatic attraction. Again, we're talking about the attraction between molecules that are permanently polar. We'll talk later about temporarily polar molecules. These are pretty weak compared to covalent ionic bonds, only about 1% as strong. If we take a look on page 451, we can see an example of the attraction between polar molecules. I'm going to show you an example as well. So notice how the molecules line up. Partial positive end of one molecule is arranged close to the partial negative end of another molecule. Let me show you what I'm talking about here. So let's say we have a hydrogen chloride molecule. Chlorine is more electronegative than hydrogen. So chlorine is able to pull this shared electrons away from, not off of, but away from the hydrogen. And because of that, the shared electrons spend more time closer to chlorine's nucleus than hydrogen's nucleus. As a result, we say that the chlorine end of that molecule develops a partial negative charge, and we can show that with our lowercase deltas. And so because the chlorine end is partially negative, the hydrogen end would be partially positive. Well, imagine you have a container full of hydrogen chloride gas. Now, we're not talking about hydrochloric acid. Remember, hydrochloric acid is hydrogen chloride gas dissolved in water. We're talking about just the gas. And so if you have a container of this gas, how are the molecules going to arrange themselves? Well, they're going to arrange themselves like this. And what do you notice? Again, we have the molecules line up in such a way or arrange themselves in such a way that the opposite ends of the molecules are near each other. I've shown as a dashed line the attraction between the chlorine end of one molecule and the hydrogen end of another molecule. This is our dipole-dipole force. Now, I don't like to use the word bond. Now, your notes say dipole-dipole bonding. This is not a type of chemical bond. This is a type of intermolecular force between permanent dipoles or molecules that are always polar. So, of course, again, if you look in the book, we do see that there are both attractive and repulsive forces between the molecules, but the molecules try to arrange themselves in such a way as to maximize attractions and minimize repulsions. All right, next up we have hydrogen bonding. Again, be careful with the name. It is not a type of chemical bond, but rather a type of intermolecular force. This is a special case of dipole-dipole force. This is an especially strong dipole-dipole force. So like dipole-dipole forces, hydrogen bonds occur between polar molecules. But this time, not just polar, but molecules that I call superpolar. This is a strong attractive force, and it only occurs between molecules that are very polar. So what kind of molecules are very polar? Molecules that have a hydrogen atom bonded to a nitrogen, oxygen, or fluorine in one molecule, that'll be attracted to the nitrogen, oxygen, or fluorine in another molecule. So hydrogen bonding occurs between molecules that have hydrogen, of course, that's bonded to either NO or F, and then the hydrogen in one molecule is attracted to the NO or F in another molecule, and vice versa. So let's take a look at an example of this. Actually, I'm going to scooch that down a little bit. Fluorine is more electronegative than hydrogen. In fact, fluorine is more electronegative than anything. It is the most electronegative element. So again, same situation we see here with what we saw with hydrogen chloride. The fluorine is able to pull the shared electrons, these two electrons here, away from the hydrogen. and it makes the fluorine end of the molecule develop a partial negative, and the hydrogen would be partially positive. Notice I drew these deltas larger to kind of show you that HF is a more polar molecule than HCl. Same thing, we get the arrangement of the molecules like this, and the attraction between the hydrogen in one molecule and the fluorine and the other molecule is called a hydrogen bond. Hydrogen bonds are typically the strongest type of intermolecular force. Little note on that later, but typically the strongest type. However, only 4 or 5 times as strong. Actually, I think that's a typo there. Let's check that out. Wording's a little weird. 4 or 5 times stronger than dipole-dipole forces, which then makes it only about 4 or 5% as strong as an ionic or covalent bond. So still, as strong as they are, very weak compared to covalent and ionic bonds. So why so much stronger than dipole-dipole forces? Has to do with the small sizes of the nitrogen, oxygen, fluorine, and hydrogen atoms. All of those are really small. Also, the large difference in electronegativity of the bonded atoms, nitrogen, hydrogen, oxygen, hydrogen, and fluorine, hydrogen bonds. Those are very, very polar bonds because of the large difference in electronegativity of those atoms. Top of page 452, again, show attraction between molecules that have hydrogen bonded to either NO or F. Strong force of attraction. Those molecules line up in a particular way. We got water on the left. Looks like we have methanol in the middle, CH3OH, and then ammonia on the right. That's red there in those diagrams. Shows a region of partial negative charge. And then blue is usually a region of partial positive charge. Graph at the bottom of page 452. This is a very important graph. I've seen this multiple times on standardized tests. We're showing a trend in properties trend in boiling point. As molecular mass increases, the general trend is we see an increase in boiling point. We're talking about compounds that have similar elements in them, or elements that have similar valence configuration. So for example, sulfur, selenium, tellurium, they all have the same valence configuration. They form similar compounds. Here we have H2S, H2SC, H2Te. We see a general increase, steady increase in boiling point as mass increases. But we see some exceptions there. We see that water, HF, NH3 don't follow the same general trend as the other elements in their group that have similar compounds, and it's due to hydrogen bonding. All right, third type of intermolecular force listed here, dispersion forces. Sometimes that term van der Waals, as you see in your notes, is a general term for any type of intermolecular forces. Sometimes van der Waals forces is specifically for dispersion. So I've seen it used both ways. So we'll just call it dispersion forces or London dispersion forces. That's why I put the abbreviation there, LDF, London, named after a scientist, not after the city. London dispersion forces. This occurs when the electrons in a molecule, primarily in a molecule, it says or ion, shift from side to side. So the shared electrons in a molecule are able to move between the nuclei of the two bonded atoms. They move back and forth. It's tug of war. So one atom pulls more, then the other atom pulls more, and those electrons shift from side to side. This is the weakest, generally, the weakest, not always, I'll explain that in a second, but the weakest of all the intermolecular forces. For comparing molecules that have about the same mass, we have something that has hydrogen bonding, something that has dipole-dipole, something that has dispersion forces. The molecules that exhibit just dispersion forces, they'd have the weakest attractive forces. Nevertheless, dispersion forces can be rather strong. This force increases when a couple things, molecules have more electrons to shift, or molecules are longer, especially if we're talking about chains of carbon atoms like hydrocarbons. Another thing to consider is the size of the electron cloud. So larger the electron cloud, the more polarizable that molecule is. So we're talking about sizes of the atoms. So the larger the atom, the larger its electron cloud, the greater the ability of that substance to have its electrons shift from side to side, creating this greater dipole moment, it's called. Dipole moment, if you recall, is a measure of polarity. We can see here in letter D, this force can become stronger than dipole-dipole or hydrogen bonding if the molecule is large enough. So again, we see this often, that we have very large molecules. They exhibit very strong dispersion forces, and that leads to certain properties, as we'll talk about in just a minute. All right, in summary, all molecules, whether they're polar or nonpolar, exhibit varying degrees of dispersion forces. As we just talked about, the larger the size, the stronger the dispersion forces. The opposite's also true. Molecule will exhibit either hydrogen bonding or dipole-dipole forces if it is polar. So please note that you cannot have both dipole-dipole and hydrogen bonding. They're related, they're similar. One's just an especially strong type of dipole-dipole force, and so it doesn't make sense to have them both. Page 454. We have some relationship between intermolecular forces and heat of vaporization, or the energy required to vaporize that substance. And so we'll talk a lot about the relationship between attractive forces and other observable properties like melting point and boiling point. So hopefully you see a trend there. Argon just has dispersion forces. Carbon monoxide has dipole-dipole, hydrogen chloride dipole-dipole, ammonia hydrogen bonding, water hydrogen bonding. So again, that dipole moment is a measure of the polarity. And so carbon monoxide is slightly polar. And then as you go down, they become more polar. And then we see the relationship to heat of vaporization. To dispersion forces, I forgot I want to show you what happens in this situation. So let's say we have a chlorine molecule. So both chlorine atoms, of course, are the same electronegativity. Bond between them is nonpolar, so those atoms share the electrons equally. So now, though the electrons will be on average found right in the middle of those two nuclei, like I said before, these chlorine atoms are playing tug of war with this pair of electrons. And so those electrons are moving from side to side between the two nuclei of the bonded atoms. Now, what happens if, let's say, the electrons happen to be on the right side of the molecule, more on the right side of the molecule than on the left? This creates something called an instantaneous dipole. For a very brief moment in time, because the electrons, shared electrons, are more on one side of the molecule than the other, this molecule becomes ever so slightly polar. And so what happens if you have a whole bunch of chlorine molecules in a container? Well, the electrons that are on the right side of this molecule are going to repel, push away those electrons, making this molecule also ever so slightly polar. So notice I drew these deltas really small. These are nonpolar molecules, but for a brief moment in time, they are ever so slightly polar, instantaneous dipole, as opposed to a permanent dipole. So you have these molecules line up in such a way that the opposite ends are arranged close to each other, and this attractive force between opposite ends of these temporary dipoles is called a dispersion force. So now think about something like chlorine versus iodine. So both are nonpolar molecules, both exhibit just dispersion forces. But with iodine, iodine is a larger molecule, has a larger electron cloud. And so we'll see, and we'll talk about in a little bit, iodine though it has dispersion forces like chlorine, its dispersion forces are significantly stronger, which leads to very different properties for iodine than chlorine. All right, I think I'll stop there and we'll continue in the next video with liquids.